The previous section showed how to get a confidence interval for the mean of a population by starting with a sample like this one and applying the mean CI function, which returns a list giving the endpoints of the confidence interval. Here's a number line plot of the confidence interval with the sample mean shown as a dot in the middle of the interval. Inside the mean CI function, the confidence interval is computed using a formula like this one, which gives the confidence interval in terms of the mean x bar of the sample and a quantity called the margin of error. The margin of error is the distance from the sample mean to either end of the interval. The sample mean is an estimate of the mean of the population. An estimate like this one is sometimes called a point estimate since it's an estimate of a particular point. The margin of error is calculated in different ways for different confidence intervals. In this example, the margin of error is computed using this formula, which gives the margin of error in terms of a quantity t star multiplied by the standard deviation s of the sample divided by the square root of n, where n is the size of the sample. The sample in this example has 9 elements, so n is equal to 9. S over the square root of n is called the standard error of the sampled statistic. The sampled statistic in this example is the mean of the sample, so this standard error is an estimate of the variability in the sample mean between samples. Standard error is sometimes denoted by SE. T star is called a critical value. The meaning of T star can be understood by considering the sampling distribution that is used in working out the confidence interval. The confidence interval considered here is a confidence interval for the population mean of a population which is assumed to follow a distribution called the normal distribution, and where both the mean and the standard deviation of that distribution are unknown. The normal distribution is the distribution with the familiar bell curve shape shown in this plot. The mean gives the location of the middle of the distribution, and the standard deviation gives the width or variability of the distribution. For a confidence interval for the mean of that population, the relevant sampling distribution turns out to be a distribution called a student t distribution with n-1 degrees of freedom. The area under this curve gives the probability of the sample statistic falling in any particular range. For a confidence interval with a confidence level of 95%, the range of interest is the range in the middle that includes 95% of that probability. The points at the ends of that range are, in fact, minus t star and plus t star, and since this is a known distribution, values for those points can be looked up in a table or calculated using a computer. Usually the table gives points such that the probability to the left of the point is equal to some specified percentage. In this example, 95% of the probability falls between minus t star and plus t star, which leaves 2.5% to the left of that range and 2.5% to the right. In the Wolfram language, a function to compute the necessary points is the inverse CDF function. This input uses inverse CDF to give the value of minus t star, which is the point such that 2.5% of the probability under the curve for the student t distribution with n-1 degrees of freedom falls to the left of that point. This input gives the value of plus t star. 2.5% of the probability to the right of t star is the same as 97.5% to the left, so using 97.5% as the second argument in inverse CDF gives the value of t star. With that value for t star, the confidence interval for the population mean can be calculated by simply substituting values into the formula for the endpoints of the confidence interval. This is the same formula that is used by the mean CI function, so this result is the same as the result from mean CI. It usually isn't necessary to memorize these formulas since they're already programmed into the computer, but there are some assumptions that came up along the way that should always be considered. In particular, there was an assumption that the population follows a normal distribution, and there was also the implicit assumption that it is possible to construct a sampling distribution. A sampling distribution is the distribution of a statistic for lots of samples, so the sample used to compute the confidence interval is implicitly assumed to be just one of many independent random samples that could have been drawn from the population. These assumptions will be considered more carefully in the next section.